Okay, help me out because we were watching the video yesterday because it wasn't working. Did we draw all four of the possibilities on how to find the reference angle based upon the quadrant? No. Just two. Okay, so let's just do all four of them again. Once you find that coterminal angle that lives between 0 and 360, then you're going to determine where that terminal ray lands. And so if it lands in the first quadrant, then the angle itself is equal to the reference angle. Because in quadrant 1, your angles are between 0 and 90, and that's what a reference angle is. It's a positive acute angle. So that's if it terminates in quadrant 1. If it terminates in quadrant 2, as we saw yesterday, this is the angle theta that gets us over into quadrant 2, but the reference angle is this guy right here. It's the measure between the terminal ray and the closest x-axis. So how do we find the reference angle in this case? Well, we see that we are stopping short of 180. So the reference angle is going to be 180 degrees minus whatever theta is, right? So if we rotate over to 170, we're 10 degrees short of 180. So you're always working off the x-axis just to kind of point out this is not the reference angle. It's not the measure between the y-axis and the terminal ray. It's always the x-axis. So you're never going to be using 90 and 270. You're always going to be using 180 or 360. All right, so now this is the new part. If it terminates in quadrant 3, I'll use blue here again. There is just a generic angle, theta, that puts us into quadrant 3. So theta is between 180 and 270. The reference angle is, again, the measure of rotation between the terminal ray and the closest x-axis. So that's that right there. So now, how do we find it based upon our picture? Now we've gone past 180 by the reference angle amount. So now theta is bigger than 180, so we still need to find their difference, but because it has to be positive, we have to do big minus small. So it's theta minus 180 degrees. Okay, the picture will tell you how to find the reference angle if you just work back to the closest x-axis. And then like the one in the warm-up that we just had, if your angle terminates in quadrant 4, then your angle is going to be between 270 and 360. The reference angle is this one right here. Again, we're working towards the x-axis, not the y-axis. And now we can find that because we're stopping short of a full rotation. A full rotation is 360. So 360 minus whatever your angle that got you there. Okay? So those are the 4 cases if you land on the interior. The special cases are if you actually land on the axes, and we'll talk about those later. Then there would be no reference angle, really. It's either 90 degrees or 0. But right now, if it terminates within the field in one of the 4 quadrants, if you could draw the picture should tell you essentially how to find the reference angle, okay? So that's why I'll always tell you on the quiz, on the test, to make sure you draw the picture. Draw your angle in standard position and then find the reference angle. So if you have an aversion to drawing pictures, you're going to have to fight through it and get over your fear of drawing pictures. Okay? They don't have to be like scary clown pictures, just cute little pictures like this. Okay? If you want to decorate them after the fact because, I mean, that's really not a picture, then that's fine. That's fine. I don't mind. You could go all Bob Ross on it if you want. Okay? A happy little tree. Uh-oh, guess what? That tree's lonely now, right? Tree's lonely. Let's put another tree back here. Little happy tree. And they're kind of hugging in their canopies right there. Kind of sweet little tree. Okay. All right. Any comments or questions on that? So just kind of review from yesterday. A reference angle can be negative. True or false? False, right. It's always positive. True or false? Reference angle can be obtuse. False, right. It's always acute. It's a positive acute angle. We're measuring a scalar quantity. We just want to know the measure between a terminal ray and the x-axis, okay? All right. Let's jump to example 6. What is that variable? Beta, right? So if beta is negative 265.363 degrees, here we go. I told you you're going to be drawing it. Draw beta in standard form or in standard position. So this one is a little bit easier than the one in the warm-up because notice it is, it's already between 0 and 360, or negative 360 and 0. So the negative means that we're rotating downward off the positive x-axis, clockwise, and that's going to put us into which quadrant? Quadrant 2? Yeah, because we go around here, that's 180. If I go 3/4 of the way around, that would be negative 270. So that is beta right there. Okay, it puts us into quadrant 2. And again, as long as it's in the right quadrant, I'm not going to make a big fuss out of it. You know, really, if it's supposed to be closer to the y-axis or x-axis, you should try to do that. But as long as you get into the right quadrant, that's really all you're going to need. All right, so that's it. That's part A. Part B, find the reference angle, beta ref. Okay. Well, let's identify what the reference angle is first. Is it this one right here, huh? Is it that one? Is that the reference angle up there? No, don't find that one, okay? It's this one here. It's always between the terminal ray and the x-axis. All right, so now how are we going to do that? If you want to, at this point, work with the magnitude of the rotation instead of the sign, remember it's a vector quantity. The negative just says we rotate clockwise. The size of the angle is 265. We've rotated past 180, correct? So if you want to find the reference angle, B sub ref or beta sub ref, again, just working with the magnitudes, you could take the magnitude of our angle, 265.363, and you could subtract from it 180, okay? And that's going to guarantee that your angle is positive, right? Again, the negative is just the direction. If you want to work with magnitudes, that's fine. And so now I guess it's time for the calculator Medora, the Explorer. Unless you want to go ahead and do good old stacked subtraction, it's not that bad. You're not going to have to borrow or anything. But I think the tendency for y'all is to reach for the calculator. Yeah, 85.363. We could have figured that out. That's just 65 plus 20 with a 363. Okay, good. We're just testing the calculator at this point to see if it's as smart as we. Yes? Yes, okay, good. Well done, calculator. So it was 85.363. Now, before you walk away, ask yourself, is that angle that I'm writing down, that I'm reporting as the reference angle, is it positive? Yes, okay. Is it also acute? Yes, okay, good. If you report a negative reference angle, it is automatically wrong. Same thing if you report an obtuse reference angle. Okay, so there's the reference angle. And that's part B. I guess we should label that part B. This is part A. Parte indeed, right? It's two birthday parties. Okay, ABC comes next. Find the coterminal angle to beta that is 47 positive rotations away. Okay, so here we go. Part C. We're finding beta coterminal that is 47 positive rotations away from beta. So let us write beta down. It's negative 265.363. And because I'm rotating in the positive direction, do I want to add or subtract rotations? Add, right? So then plus 360 degrees times 47. Yeah, that's all you have to do. Remember, there's infinitely many coterminal angles for any given angle, including coterminal with itself. All right, so there's your setup. You write it down on your iPad paper, and then you go to the calculator. Let me just kind of keep this split screen here. All right, so now we can just type that in there, negative 265.363 plus 360 times 47. And we write it down. It is 16654.637. And once you write that down, are you good right there? Is that your final answer? No. What are we missing? Yeah, degrees. The unit, right? The Grubble. You don't want to miss points for missing that. That should be pretty easy. Okay, cool. So that's kind of reviewing what we've already been doing. That's part C. Part D, now it says to convert beta, beta ref, and beta coterminal into DMS notation. Oh, okay. We could do that. A, B, C, D. So beta is, let's see, you could do this one of two ways. You could do it the way you did it yesterday on the quiz. You could just take 0.363 times 60, and then that fractional part times 60. But I did tell you that once you did it on the quiz, if I ever asked you to do it again, you could just let the calculator do it for you. Do you remember that? And that's true. So if you want to type that angle in, then you just go to your angle menu, which is second EPS, column 2, row 3, and then select number 4, and there it is. So that's negative 265 degrees, of course, 21 minutes, and then 46.8 seconds. Remember, if there's more than 3 decimals on the seconds, we just report 3 decimals. We don't go down to a smaller unit. Okay, so there's beta, equivalent to, and now let's do the reference angle. All right, do we need to pick up the calculator and do it again for the reference angle, or can we figure it out? It has the same decimal part, right? Beta was 0.363, and that decimal part turned into 2146.8. The reference angle is also 0.363, so it should have the same minute second. So if you wanted to type it in again, you're more than welcome to, but that would be 85 degrees and then 21 minutes, 46.8 seconds. Okay? It's good to be aware of things, like poles right in front of you. All right. And now the last one is the coterminal angle. The coterminal angle. Now the coterminal angle had a suffix or a decimal part of 637. So that one's different. So let's just go ahead and type that one into the calculator. You can actually leave off the 16654 part if you wanted to, couldn't you? Yeah, save some keystrokes. We're really just interested in the 0.637. So if you want to do just 0.637 and then go to second angle number 4, hit enter, and there it is, 0 degrees, 38 minutes, 13.2 seconds. Well, we know it's not 0 degrees because we had, bless you, yeah, bless everybody. So you're going to write down 16654 because that's full degrees, and then you're going to put 38 minutes and 13.2 seconds. Now, of course, you don't have to do it the way I just said. You could actually just every single time type in the entire angle and then go to option 4 and convert it, okay? So there they are. Blah, blah, blah. Yeah, and that's it. That's just a question that kind of puts everything we've been doing into one problem. Mosquito. There you go. Yeah. Take a picture for the scrapbook, the digital scrapbook. Yeah. No, that's good. That's good. That's good. You have a record that I was actually teaching today in case administration wants proof. Thank you. Yay. Yeah. Okay. Any questions so far? Okay. So kind of shifting gears here a little bit. We have been measuring our rotations, or the amount of rotation in degrees. What are the units of degrees? That's a trick question. Degrees, right. Degrees are very specific units. So if you are ever doing calculations that involve things that rotate, whether it's like an engine part rotating or a Ferris wheel rotating, or even like tides rolling in and tides rolling out, things that, occur cyclically, using degrees doesn't work, okay? When you're working with like distances, like how far someone travels along an arc, you can't use degrees because distance is equal to rate times time. The units have to work out. So if you're talking about a rate, that would be like miles per hour times time, that would be hours. Your hours divide out and you're left with miles. So if you ever are doing calculations that involve length or distance for things that rotate, like arc length, you're going to end up with like miles degrees, and that doesn't make sense, right? Like, how far is it from here to San Antonio? Oh, it's about 30.2 miles degrees. People are like, what did you just say? Right? It's like, are you trying to tell me the temperature and the distance at the same time? No. See, it makes no sense. And so we need to come up with, invent, if you will, another way to measure rotation. A way that doesn't have units associated with it. Boy, that seems like a tall task. Right? Are you ready for that task? We are going to invent another way to measure rotation that does not involve units. Okay. Let's go ahead and introduce what's known as a radian. Okay? Now, if you've had science class, you probably already have used radians, but you're like, I don't know what a radian is. We're just using them. Yeah, right? I ask students all the time, how's science going? It's going great. We're using radians. What's a radian? I don't know. We're just using them, right? Okay, cool. You never introduce yourself to each other. You're just using them, right? You don't want to use them, right? Get to know them a little bit. So if you look at the word radian, it almost, if you're really bad at reading, you might actually read that as what? Well, that's a loaded question. Radius, right? Radius, right? And that is not by chance, because a radian, as it turns out, is going to be that unitless measure of rotation that we're not going to invent it, but I'll construct it for you. And it is intimately tied to the radius of a circle. And so that's why we've kind of changed the letters at the end of the word radius and made it into radian. All right, so let's look at a circle. Here's a circle. Everyone see that circle? It's in your notes. Let's say the circle is arbitrarily big or arbitrarily small. You can make it as big or as small as you want, right? Look, see? We can make it as big or as small as we want, so long as it fits still on planet Earth, right? We would hate our circle to have to go all the way to Jupiter. That'd be kind of big. But once you have established the size of your circle, there is a radius associated with it. If we center the circle at the origin of our coordinate plane, the radius we can define as little r, right? And notice as you rotate all the way around 360 degrees, if you were a point on the end of that radius, you would scribe out that circle, yeah? This right here is then going to give us a terminal ray. The radius becomes a terminal ray that defines an angle in standard position. We call this angle theta, we call it the central angle. Why in the world would we call it a central angle? Where is it located in respect to the circle? It's in the center, okay? And that's going to end up being our reference angle. Okay, so if you are measuring then how far you travel along the outer surface of the circle, we call that the arc length. Okay, and it is a distance. And for some reason, we use the letter S to represent arc length. Because if you read arc length very carefully, you'll hear that S sound, right? Arc length. No, it's not in there. No, it comes from the Greek stadia, which is what they used for their measurement of a mile. So it's S. They didn't want to call it A because A is typically area. In calculus, though, we call it script letter L for length. But anyway, we're going to call it S. All right. So here's what's cool. If you take any circle, regardless of how big or how small, and you then take a rope that is exactly as long as the radius, okay? You take a rope that is exactly the length of a radius. If you started laying that rope along the circumference of the circle, okay, it's going to then be able to bend along the curve because it's a rope, right? This would end up being one radius length, okay? If you take the length of a radius and you wrap it around starting from the standard position and you wrap it around the curve, that length, one radius, then forms this little piece of the pie, right? This little piece of the pie right here. I don't know, you can see that. I have to double highlight it. It gives us that right there. That central angle that subtends the arc. That's a new word, subtends. What does sub mean? Sandwich? It's below, right, subtends. So we say that that angle subtends the arc. The arc is above it, the angle's below it. Okay? That angle, that is exactly one length of the radius for any circle, is going to be defined as 1 radian. Okay? So in this case, theta equals 1 radian. Okay? And it's simply because it's 1 radius length along the arc. Now, it just so happens that if your circle happened to be bigger, if you want to draw just a slightly larger circle around the perimeter here, something like that, the radius is now going to be bigger, no doubt. Okay? The radius is now bigger. But if you still took then that length of the radius and you started wrapping it around its circumference, guess where it's going to end up? It's going to end up at the same place. Okay? It's going to end up at the same place. And so the measure of that subtended angle is still going to be the same size. And we call that 1 radian. All right? Now, for any circle, regardless of size, how many lengths of a radius can you wrap around itself? Well, it turns out that if you go another length of a radius, here's like 2 radians, right? 2 radius lengths. If you draw a line back to the center there, here now is the angle that subtends that arc. Guess what the measure of that angle is? That would be 2 radians. Okay? If you wrap another length of the radius around, you're going to land up right here. That's 3 radians. It's going to end up just short of 180. If you draw that line back to the center, then that angle that gets all the way over there is going to be called 3 radians. And we'll keep going. Okay, you go again. There's 4 radius lengths. So that angle there is 4 radians. You keep going again, and you get about over here. So that angle that gets all the way around to there is going to be called 5 radians. You're going to go again, and you're going to get to about right here. Okay, you go all the way around to there. That's 6 radius lengths around the perimeter. So that's going to be called 6 radians. And then you're going to have this little bit left over. And so this is true for any circle. For any circle, regardless of how big or how small, you are always going to be able to fit 6 full lengths of the radius around its perimeter, plus a little bit less than half, a little bit more than a quarter actually, okay? A little piece left over. Now, why is the radian unitless, okay? Let's go ahead and define it. A radian is the measure of the central angle of a circle subtended by an arc equal in length to the radius. That's what we just said, right? Take one length of the radius, that arc defines then a pi wedge. The central angle is called 1 radian. We say then that the measure of an angle in radians in standard position, this is important, it's the ratio of the arc length S to the radius R of the circle, okay? In other words, we can define it by this formula. This is the formula that defines a radian measure, okay? So let's see. Let's say example, I have a radius of 5 inches, okay? If I have a radius of 5 inches. Let's just quickly draw this circle. There's 5 inches, okay. If I come around here then and I go 1 radius length, then my arc length is 5 inches, yes? I've traveled around the perimeter 5 inches. Well, what's the radius equal to? 5 inches. So, according to that formula, that angle right there, theta, is going to be the arc length distance, which is 5 inches around the perimeter, divided by the radius, which is also 5 inches. Well, first of all, what happens to the units of inches divided by inches? They divide out. And then 5 divided by 5 is 1. So this is why the radian is unitless, because the units are always going to divide out, because we're just taking the ratio of a length to the radius length. Okay? Now, if we just write 1 out there, if we put theta equals 1, how are you going to know if that's in degrees or radians? If I just said theta equals 1, how are you going to know if that's in degrees or radians? You actually do, right? Is that degrees? No. How do you know it's not degrees? Yeah, there's no degree bubble, right? There's no degree bubble, which is why it's important if you are in degrees, you make sure you put the degree bubble. So in the context of an angle, if there is no degree bubble, you're like, oh, it must be our unitless measure of rotation called the radian. Now, what we typically do is we write rad behind it. That's helpful. That's not a unit. It's short for radian, but it's a description that helps remind us that we're in the context of an angle, okay? All right. Let's go around just real quickly here. I'll do in green. Let's go around another length. So what would my arc length be if I go around 2 radius lengths? It would be 5 inches. 5 inches, that would be 10 inches, right? So what is the measure of this? Well, by definition, it's the arc length, which would be 10 inches around the perimeter, divided by the radius, 5 inches. The units divide out. 10 divided by 5 is 2. So there you go. Go all the way around. Okay, so now that we know what a radian is, it is a ratio of an arc length to a radius of any circle. And regardless of how big or how small, that measurement of the central angle is always the same. Because they're both linear, it increases or decreases proportionally. And that scale factor will always divide out. Okay? Now the question is, how can we figure out a conversion between radians and degrees? If what is true, or if it's true what I told you, and it is, that you can see it right here, for any given circle, you can go around 6 full radiuses, right? There's 1, 2, 3, 4, 5, 6 of them, plus a little bit left over. We want to then figure out a conversion between degrees and radians. So it would appear that one rotation is about 6 point something radians. And we also know that one rotation is 360 degrees. So if I can figure out what that decimal is, I will have a way to convert between degrees and radians. But it's not good enough to say 6 point something something is 360. That doesn't really do much for converting. So how can we figure out what a radian is equal to? Well, I will show you. Okay. It says, use the equation for the circumference of a circle with radius r and the definition of the radian measure to determine the exact and approximate radian measure of a full rotation. All right, so let's go ahead and do that. First of all, theta is equal to s divided by r. Yes? Okay, and theta is going to be in radians, which again is not a unit, it's just a description, right? It's a description. We also know then that in a circle, the circumference is equal to what? What formula have y'all memorized? Yeah, it involves pi. 2 pi r or pi d, right? Pi times the diameter. This equation has been around for a long time. In fact, Archimedes, way back in ancient Greece, Archimedes, there we go. He's on the poster over there. He kind of came up with this and actually proved it. So this is known to man. Well, what is the circumference? But the arc length for a full rotation. Would you agree? Yeah, the circumference is really just the arc length for a full rotation. So let's go ahead and see then what the radian measure is of a full rotation. So for one full rotation, we get theta is equal to, of course, s over r. But as we just said, what is the name for the arc length of a full rotation of a circle? It's the circumference. So it's really c over r. Well, using Archimedes' formula, what is the formula for circumference? 2 pi r. So we get 2 pi r over r. And lo and behold, what happens to the r's? They divide out. And we get 2 pi radians. Oops, misspelled radians. 2 pi rads. And that does it. One rotation then, we have it now. One rotation is equal to 360 degrees, and one rotation is equal to 2 pi radians. Therefore, by the transitive property, so 360 degrees must equal what? 2 pi radians. Well, guess what 2 pi is approximately? What is pi approximately? 3.14. So 2 times 3.14 is about 6.28. Remember I said for any circle you can get 6 full lengths of the radius plus a little bit more? Guess what that little bit more is? 2/8, right? It's a little bit less than a third of another length of the radius. Okay? Now pi is an irrational number, so it's non-terminating. So that's 6.28 blah 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 blah. But if we let it be represented by pi, we can have an exact value. Okay? In fact, if I say 360 equals 2 pi, I can divide both sides by 2, can't I? And I can say then that 180 degrees is equal to pi. Yeah, and so if you look at this picture over here, here's 180 degrees. You can go 1 radius, 2 radiuses, 3 radiuses, and then 0.14 of another. So this becomes our conversion factor. You could also divide by 2 again. 90 degrees is equal to pi halves. But that one has a fraction in it. Okay? Yeah. So this right here becomes our conversion factor. And just like we did with degrees and minutes and seconds, we can write it as 180 degrees over pi radians, or we can write it as pi radians over 180 degrees. So depending on whether we're converting from degrees to radians or radians to degrees, we would want either the degrees to divide out or the radians to divide out. We could use either one of those 2 conversion factors. They're equivalent to 1. All right, so now you know what a radian is. What are the units of radians? Nothing. Good. Radians are unitless. So when we say rad, we just mean a description to remind us that we're talking about rotation. What are the units of degrees? Degrees, right. Okay, cool. That's a major breakthrough. There it is. There it is in a chart. Okay, there it is in the chart. Okay, so let's go ahead and do example 8. It says convert the following angles from degrees to radians. Leave pi visible in your answer. Okay, I'm going to draw it first. 90 degrees is right here. Okay, 90 degrees. But I want to know how many radians that is. So here's what the conversion will look like. You're going to memorize this soon enough. But again, if you put it over 1, we're going to multiply by a conversion factor. We want to convert it to radians. So to get the degrees to divide out, degrees have to be in the bottom, and that means rad has to be in the top. So what's the conversion factor? Pi over 180 or 180 over pi? Pi over 180. By the way, you could still use 2 pi over 360. That's fine if you want. But pi over 180 is simplified. The factor of 2 is divided out. So it's the simplest conversion factor that doesn't have like a pi halves of 90, like fraction in it. All right, so if you do that, those divide out. And we want to leave pi visible in our answer. So what we really want to do is simplify this. What is 90 1/80ths? What does that simplify to? 1/2, right? So if we multiply across, we get 1 times pi is pi, 1 times 2 is 2. And as we already kind of saw, 90 degrees is equal to pi halves radians. They are the exact same. Pi halves is 90 degrees. 90 degrees is pi halves radians. Okay? So if we're going to have to memorize those, you might want to just memorize it now. All right? So cover your eyes. 90 degrees is Pi halves. Good. You already have it memorized. Sweet. What would 45 degrees be? Pi fourths. Good, because that's half of 90. That's half of pi halves. Sweet. All right, 180 degrees. We don't need to do anything here. We know that's pi radians. Okay, pi radians. Go ahead and do this one. 270. Convert it to radians. Again, your conversion factors are either pi over 180 or 180 over pi. You'll know which one to use because you'll need to divide out your units of degrees. Yeah. Yeah, typically we put the number in front of pi. Yeah. So if you can't simplify this in your head, the zeros divide out, so it's really 27 1/80th. Since we want to leave pi visible in our answer, because again, if we don't, it's going to be an ugly decimal that we'll have to round. When we have an angle in radians, we prefer to leave pi visible. So you could do this on your calculator: 270 divided by 180. Hit enter, and then of course you can just hit math, and there's that convert to fraction. Enter, enter. So if you want to do that, that's fine. Okay? And so now it's 3 halves times pi. 3 halves times pi. But the way we prefer to write it is not 3 halves times pi. We prefer to write it as 3 pi halves, right? Or, and again, we don't use 1.5 pi. That's equivalent. But we're going to be working with a lot of fractions involving pi. You're going to memorize what's called the unit circle. You may have heard the legend of the unit circle. Okay? Yeah. We're going to memorize that. So 3 pi halves is one of those angles like 90 degrees and 180 degrees that lands on a quadrant. Those are called quadrantal angles. And you're going to have to memorize those. So 0 degrees is 0 radians. 90 degrees is pi halves radians. 180 degrees is pi radians. 270 degrees is now 3 pi radians. 3 pi half radians, sorry. And then 360 would be what? 2 pi radians. Yeah. And again, you don't have to write rads after it, right? You don't have to write rads after it. It's just helpful to do that because it keeps you in the context of rotation. 2 pi itself is just a number, okay? All right, let's see if we can stop there for, let's do one more. Let's do the top row, 60 degrees. Go ahead and do one more, 60 degrees, convert it. This is another one that we're going to end up memorizing. 60 degrees lives somewhere up here. If you notice how I write my pies, I don't put the squiggle on the top. I just put a straight line. If you are more artistic, you could do the pie like that. That's fine. Yeah. If you convert it, multiply by pi over 180, 60 1/80th simplifies to 1/3. But another way to do it is say, oh, a full rotation is 360. 60 degrees is a sixth of that, right? So what's a sixth of 360? A third. So it's pi thirds. So 60 degrees is pi thirds radians. Pi thirds radians is 60 degrees. They are the exact same angle, and we will stop there.